Welcome back, everybody. This is our third session in NEET previous year questions for chapter Electromagnetic Induction of class 12th. Before this video, we have made two videos in this series, and all of those videos are available on channel's playlist section. We have also started similar series for JEE mains. So if some of your friends are preparing for JEE, then they can also watch those videos, and you can also get a handy practice from JEE videos. If you find these videos useful, helpful, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, let's start today's video. And in the previous one, we completed up to question number 17, I think, or 17, yes, it was 17. So that was the last question. Let's start with the next one. So here we have the magnetic flux through a circuit resistance R changes by amount delta phi in time t. Total quantity of the charge that passes at any point in the circuit during the time is represented by. So we have to find total amount of charge, and that can be get as induced EMF E is equal to minus d phi by dt. Now we can write current from this. Induced current will be induced EMF by R, so it will be minus 1 by R into d phi by dt. And we know that current is rate of change of charge, so it will be dq by dt is equal to minus 1 by R d phi by dt. That dt gets cancelled, and dq will be minus 1 by R into d phi, integrating both of these sides. So we will get Q is equal to 1 by R into phi, or we can say delta phi, change in flux. So here is option B will be the right answer for us. Let's move to the next one. The length of a conductor of length zero point 0.4 moving with speed 7 perpendicular to magnetic field intensity. This induced EMF we have to find, and we know that induced EMF is given by BLV, where B is this, so 9 into 10 raised to power minus 1, length is 4 into 10 raised to power minus 1, and velocity is 7, so this will be 36 into 7, that will be 252 divided by 100, so 2.52 volt will be the answer here. Let's move to the next one. Let us consider two solenoid X and Y made of same magnetic material. So material is same, equal area of cross section is same, length of X is twice that of Y, and number of per unit turns of X is half that of Y. So we can say length of X is twice the length of the Y, and number of turns per unit length in X and X is half that of Y. So it is half of Y. The ratio of self-inductance of the two solenoids. So we have to find ratio of self-inductance. Now self-inductance is given by mu node, and where small n is the number of turn per unit length into area into length. Now their material is same, so mu node is same and area is same. The only difference is n and l. So Lx by Ly will be nx square by ny square into Lx by Ly. So that will be Nx by Ny whole square into Lx by Ly. From this, Nx by Ny is half, and square of that is 1 by 4 into Lx by Ly will be 2. So it will be 1 by 2, or answer will be 1:2. Let's move to the next one. The magnetic energy stored in an inductor of inductance 4 microhenry carrying current of 2 ampere So we have to find energy of inductor, that is given by half Li square. So half L is 4 into 10 raised to power minus 6, and current is 2 into 2 square it is. So it is 8 into 10 raised to power minus 6 or 8 microjoule. Moving to the next one. Two conducting circular loop of radius r1 and r2 are placed in a same plane with their center coinciding. If r1 is greater than r2, mutual inductance between them will be directly proportional. So we have to find out coefficient of their mutual inductances. So let us draw the diagram first. So basically we have two coils. Suppose this is our first coil, the smaller one, and then we have a bigger coil of different radiuses. Now radius of the smaller is r1 and that of bigger is r2, and we have to find their mutual inductance. Now we know that for self inductance phi is L times I, and in case of mutual inductance the flux associated is M times I. And while doing this type of calculation, what we assume, even if we have been given current in the smaller ring, then we take the same current in the bigger ring. And that is why. Why? Because uh, when we calculate the flux, we need a magnetic field. And that magnetic field needs to be constant. If we take current in the bigger ring, suppose this is current in the bigger ring, that is I, then inside it, inside the we can say nearby the center of the magnetic center of the bigger ring, which is also the center of the smaller ring, the magnetic field produced by the bigger ring will be almost constant. But we cannot say this in case of that if we have a current in the smaller ring, then outside it magnetic field will be variable, and mutual inductance this coefficient of mutual inductance is constant. So we can either calculate it by calculating flux with the bigger ring or with the smaller ring. In case of smaller ring, it becomes quite easy to do the calculations. So that's why we assume that current is in the outer ring and the radius r2, here we have, okay, r1 is outside, so that is r1, and radius r1 is very large as compared to r2, so that the smaller ring is just about the center of the bigger ring, and magnetic field value is almost constant here. So now flux in the smaller ring will be given by magnetic field around smaller ring into area of the small ring. Now this magnetic field is being produced by the larger ring. So magnetic field will be mu node I by twice of R1, because radius of the bigger ring is R1. So twice of R1 multiply area of the smaller one, that is pi R2 square. So this is the flux, and that flux should be equal to mutual inductance times I. So we can say it is M into I. So I get cancelled, and M is proportional to R2 square by R1, and that is option D for us. Let's move to the next one. The magnetic potential energy stored in a certain inductor is 25 millijoule when the current in inductor is 60 milliampere. The inductance of the inductor. We know that energy stored is half Li square in case of inductor. So it will be 25 into 10 raised to power minus 3 is equal to half. L is 60 into 10 raised to power minus 3 into I square, 10 raised to power 3 get cancelled. This is 50 by 60. I think, okay. So we have to find L and sorry, I wrote it wrong. This is I. So again, I square we have, so it's 16 to minus 3 into L we going to have. So 10 raised to power minus 3 is cancelled, and we are left with 50 divided by 60 with 10 raised to power minus 3, and this is equal to L. So it get cancelled, and we will have 5 by 36 into 10 raised to power 2 here. So that will be, we can write 500 by 36, and solving this we will get 13.9 Henry almost. If we want to approximate it, we can approximate it to 40. So that will be 500 by 40, 25 by 2, or 12.5. The nearest possible, that is 13.89. So option D will be the right answer here. Let's move to the next one. A solenoid has 1,000 tons current 4 ampere flows through it. Magnetic flux linked with each turn of the solenoid is this self-inductance. So self-inductance we have to find out, and we know that total flux is equal to L times I. Here total flux will be 1,000 times the flux through one coil. So 1,000 into 4 into 10 raised to power minus 3 is equal to L, and current is 4. So coefficient of mutual inductance will be 1. So option C will be the right answer. Let's move to the next one. Current given coil of inductance this Henry, the magnetic flux linked with the coil. So we have to find out magnetic flux, and that flux is given by phi is equal to L times I. So at L is 5 and I is 2.5, so it will be 12.5 Weber. Option C. Next one, the current I in the inductus is vary according to this plot. So this is our source current, and we have to find out correct variation of voltage with time in the coil. So voltage induced inside the inductor, that is given by minus L di by dt, and here we are discussing about the induced voltage, as it is not mentioned in the question, but normally we assume it will be induced voltage. So let's mark some point O, point A, point B. So between O to A, current is increasing linearly, or we can say di by dt is positive constant. So VL will be, the induced EMF will be the negative, and that will be constant also, as di by dt is, we can say, uh, is positive constant. So graph should be like this. Induced EMF will be initially should be negative up to point A. Now after that, it current starts decreasing. If current is decreasing, means di by dt is negative, and if it is negative, this whole term will be positive. So our graph should become positive like this. And none of our answer matches it, but the most accurate, we can say most nearby, if we multiply it with the negative one, then our graph will reverse, and our graph will look like this. In that case, we can mark that option D will be the right answer. Let's move to the next one. Here again we have I variation, and we have to find out the EMF. And this variation is along the coil. And we know the coil is also a inductor. Coil is actually also an inductor. So, and we know induced EMF in case of inductor is minus L di by dt. This is the induced EMF. So again, if we uh, mark some point here, point O, A, B, and C. So from O to A, the current is increasing linearly, and it is increasing, so di by dt is positive, so induced emf should be negative in this region. So here we should have negative induced emf. From a to b it is constant, so di by dt is 0, so here we will have 0 induced emf. And b to c di by dt is negative, so here we will have positive induced emf. And this is also constant, this is also constant, as di by dt is increasing and decreasing at a constant rate. And if we match this, then option d, where initially we have negative constant emf, then it becomes 0, and then it becomes positive emf. So option d will be the right answer here. Let's move to the next one. Two coils of self-inductance 2 and 8 millihenry are placed together so that effective flux of one coil is completely linked with another coil, the mutual inductance of these two coils. So if we have value of mutual, we can say self-inductances of two coils, then their mutual inductance is given by K under root L1 into L2, where K is the coupling constant. As it is mentioned that there is complete coupling, so we can say K is equal to 1. So it will be 2 into 10 raised to power minus 3 into 8 into 10 raised to power minus 3. So 16 into 10 raised to power minus 6, and root of that will be 4 into 10 raised to power minus 3. So 4 millihenry. That is option D for us. Let's move to the next one. In an inductor, self-inductance is 2 millihenry. Current changes according to this relation. At what time EMF will be 0? So EMF or induced EMF is minus, it is inductor, so minus L di by dt. So minus of 2 into derivative of this value, it will be first taking derivative of t square, so 2t into e raised to power minus t plus t square as it is, and derivative of e raised to power minus t, that will be e raised to power minus t into minus t's derivative minus 1. So we can take e raised to power minus t common out of this. So minus 2 e raised to power minus t. We have 2t here and minus t square here. As per mentioned that EMF should be 0. So EMF should be 0. EMF will be 0 when either this term is equal to 0, and to reduce this term to 0, we need that e raised to power minus t is equal to 0, or we can say 1 by e raised to power t is equal to 0. In that time t will be infinite, and we can't see any option as t is equal to infinite here. So then we will reduce this term to 0, and this term will be 0 at 2t minus t square is equal to 0. So 2t is equal to t square and t is equal to 2 second. That is the possible option in option C. Now let's move to the next one. A varying current in coil changes from 10 to 0 in 0.5 second. Average induced EMF is 220 volts. The self-inductance we have to find out. So again, induced EMF is minus L di by dt for inductor. This is mentioned to be 220, and L we don't know, and di, that will be change in current, that final is 0, initial was 10, so it is minus 10. By time it took is 0.5, so it will be minus minus plus, 0 gets cancelled, and this is half, multiply into 22. So L will be 22 into half, that will be 11 Henry. Option C will be the right answer. Next one. The number of turns per unit length of a coil of a solenoid is doubled. Self-inductance of the solenoid. So we know that self-inductance is mu node n square A L, where n is the number of turns per unit length. If we double this, then we will get 2n square, or L becomes 4 times. That is option D. Next one. So variation of EMF with time for four type of generator is shown in the figure. Which among them is called AC? So we know that AC is a sinusoidal shape, and this will be AC, and this is square wave, this is a triangular wave, and this is also a triangular wave. So only option 1, option A will be the right answer. And this is also AC, this is also AC, and this is also AC, and we can say this is also AC. All of these are AC. They can be represented in a different form. So let's move to the next one. A wire loop is rotated in magnetic field, frequency of change in direction of the induced EMF. So we have to find out frequency of change in the EMF. Now we know that EMF will be minus d by dt of the flux, and here flux is B dot A, and A, as loop is rotating, A will be A node into cos omega t. So it will be B A node omega sine omega t. So our rotation frequency was, angular frequency was omega, and frequency of EMF is also omega. So we can say frequency will be same, and the frequency of change in direction of the induced EMF is here it is not clear that how many number of rotations are there. So we suppose we have a one rotation per second. So we know that in this one rotation, this sine omega t will vary from +1 to -1, means current will change its direction twice. So according to one rotation, answer will be twice per rotation. Now let's move to the next one. A sheet is placed on the horizontal surface in front of a strong magnetic pole. The force needed to hold the sheet if it is magnetic, hold the sheet if it is not magnetic, move away the sheet from the pole with uniform velocity if it is conducting, move away from the sheet away from the pole with the uniform velocity if it is both conducting and not conducting. Now we know that magnetic forces are applicable only on the magnetic materials. So that magnetic force only acts upon magnetic materials. And if we have a non-magnetic material, then it will not be affected by neither magnetic field nor by the magnetic material. So as mentioned that we have a strong magnetic field here, so it will be only applicable on magnetic type material. So B is cancelled out, that it is a non-magnetic, and sorry, second is cancelled out due to non-magnetic, and fourth is also cancelled out, as here again non-magnetic and non-polar, non-conducting and non-polar are mentioned. So we are only left with the magnetic type material. So 1 will be true and 3 will be true. Why? Third will be true. Why? Because in third we have been given a conducting sheet which is moving with some velocity. So it will act as a conductor of some length moving with some velocity in a magnetic field. So there are chances that there will be induced EMF and there will be some force acting on this conductor depending upon the orientation of the magnetic field length and the velocity. So we can say option A, 1 and 3 are the possible answers for which can be true. And let's move to the next one and the last one. In which of the following devices eddy current effect is not used? So eddy current effect is not used means in eddy currents normally we cancel eddy current by separating the device into smaller parts, and that we can see that in case of in case of electric heater we use some wire of some specific resistance, and due to flow of current this wire generates heat, and this is joules heating law. So option C is the point where we don't use eddy currents. So with this we end this video here, and all the questions are also completed. So again, if you find this video useful, helpful, then do press the like button, share it as much as possible, and subscribe to our channel. Also, if you like to support us financially, you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help or amount will be highly appreciated. So again, thanks for watching, and we will meet in next video.